Okay guys, in this video lesson we're going to take a look at center of mass and how it pertains to momentum, and in particular rotating momentum. Okay, so what we're going to get into is what is center of mass, and then talk about how things when they fly through the air as projectiles rotate about their center of mass. Okay, so first thing, what is the center of mass? So the center of mass on any object is that point that indicates its position. Seems kind of weird, but really you could say it's the middle, but it's not always the middle. You could say it's the part where all the masses equal each other if you do all the vectors inside, but that gets confusing. So really what it is, if we were looking at any massive object, this rock balancing on top of this here, if we wanted to identify this entire rock having a single position, we would put it at the center of mass. All right. The reason why is because that's going to determine all of our balance and our flight patterns of that object. Okay. Now, if you do have a solid, symmetrical, uniform shaped object, it's in the center of it. Okay. So for example, we have this disk down here. Okay. If I want the center mass of this, assuming all the blue stuff is of equal composition, my center mass would be right there in the dead center of that disk. Okay. But it doesn't need to be in the center, and it doesn't need to be on the inside of the material. Okay, odd shapes, hollow things, center of mass can actually exist not even on the object. So for example, if we have a ring now instead of a disk, if this is empty space inside of here and we want to find the center of mass of this ring, it would still be right there in the center, even though it's not even on the object itself. Move over to this thing. I don't even know what this thing is, but whatever this thing is, if I wanted to find its center of mass, it might be here, it might be outside of here, it might be down there. I don't really know for sure. So when we look at something like this, we don't want us to think that center of mass is always in the middle of something. It's the point at which we have this position indication. Now, we can always find center of mass, and there's a couple different ways we can do that. Okay, the first one actually centers around this rock sculpture we see here. Now, I believe that they actually drilled into these rocks and put a bar between these two things to get them to balance. I don't know if they actually sat them here and have them perfectly balancing. That'd be pretty impressive if they did. However, they are using center of mass to help line this up. Okay, and if I want to know where the center of mass is on this object, because it has a single contact point, I know the center of mass resides somewhere along this vertical axis. Okay, I don't know for sure where, top to bottom, but somewhere along this, because the center of mass has to be over top of my contact point for me to have that balance to occur. So when we start looking at center of mass and how we locate it or where it is, we have a couple of things to think about. First of all, our center of mass determines our balance or our stability of an object. Okay. That means if we have one point of contact, okay, a single point of contact, you have 1 foot, you're on the ground. You have just a point of something, a single point of contact, the center of mass should be sitting over top of that or directly over that, and that we call that being balanced. All right. If you have a center of mass between multiple points of contact, which means let's say you have 4 wheels to a car, or 3 legs to an end table, okay, or us on our own 2 feet. That means we have a certain amount of stability, and our center of mass has to be between those points of contact, not in the middle, but someplace between them for us to be stable. Okay. Here's a site for us that looks at stability. Okay. Now we have 2 different cars here. This car would be less stable than this one because it's much more narrow, so its points of contact are closer together. And this black dot here represents our center of mass is higher than this one. So a lower center of mass in a wider base gives you more stability. That's no different than your coaches who ever told you to get lower and get your feet wider. The reason why they're telling you that is they want to bring your center of mass down lower, and they want you to have wider feet so you have a bigger base. They're trying to increase your stability as you perform. Okay. Here's an interesting thing. As soon as your center of mass gets outside of your stability point, you fall. Absolutely fall. Okay. Doesn't matter how strong you are, doesn't matter how tough you are, doesn't matter how flexible you are, doesn't matter how good your core muscles are. If your center of mass goes outside of your stability points, you fall. Now, as people, we do lots of things to constantly stay balanced or stable. We do that by constantly shifting our weight or our center of mass around our body. Okay, so as we bend over to pick something up, we stick our butts out. Okay, we just do. Try it at home. You can't bend over and touch your toes if you put your heels and your back against a wall. Try it. Okay, you can't. You'll fall over, on your face. Those kind of things. Because for a person to bend over and touch their toes, for them not to fall forward, they have to push their hips and their butt backwards. They just have to. Okay. Now, for inanimate objects like these cars, this double-decker bus, if they were ever to have their center of mass move outside the wheels of those things, it would fall over or tip over. That's why tall vehicles have more of a risk of rolling over. Okay, a much lower sedan or kind of sports car sits really wide, has a low center of mass. It takes a lot of tipping before it's actually going to fall over. Okay. This is another good example of that. We have 3 stools, and we have a wide base, medium, and a narrow base. If they're all at the same angle, this stool, if we let go, would land back on its leg. This one would barely land back on its leg. This one, it would fall over this way because its center of mass is no longer located inside its stability points. Okay, so that's what we mean about being stable. Now, the other thing a center of mass does for us, it also determines our rotation point. Okay, if I want to take something and throw it through the air. Now, if I throw a ball or a frisbee, those things travel because they have an equally distributed mass pretty much through a normal projectile motion. However, if I want to chuck a hammer, or I want to throw a boomerang, or I want to throw some other object, let's say you want to flip a bottle and you want to do bottle flipping and try to land a bottle flip. They don't rotate and fly the same as a baseball would. The reason being is they're going to rotate about their center of mass, not their middle point. Okay. So what we can do is, if we're trying to find the center of mass on something, we actually can track where that center of mass is located by watching how it rotates. Here's a video from MIT that allows us to show this idea of center of mass. You'll notice with these throws, you can see that the objects are not symmetrical. So they kind of spin in weird shapes as they fly. Now they're going to move it under a black light and only have the center of mass painted in orange for us. These are the same objects you saw before, but now they look like they're flying under a normal parabolic motion because we don't see the rotation, all we see is the center of mass in that orange dot. They're going to change it up for us now and give us this disk again, and they actually have the dot on the center of the object, not the center of mass. Notice the wobble in that throw. Now at the center of mass, notice how it doesn't have that wobble anymore. Okay? Okay, so what that tells us is that as things fly and they rotate, they're going to rotate about their center of mass. That becomes important to us because the next topic we're going to talk about is what happens as things rotate through time and how can we track that in terms of momentum. Thank you.